Hello and welcome to the first section. Together, we shall embark on a journey through the advanced and the complex generative adversarial networks. We will learn the basic building blocks that you can stitch together to build any kind of GAN you dream of. This section is a refresher on PyTorch deep learning library, but you will find it amusing even if you are already familiar with PyTorch. This section concludes with a video lecture on how to build a custom loss function. This skill is essential for developing your own GANs and in general deep learning solutions. In the first lecture, PyTorch forward and backward propagation, we shall review the very first basics of deep learning and implement LeNet5 architecture. Let's get started. In order to get the most out of this course, I have a few hints for you. First, download the course materials and the coding exercises and open them on another screen as you watch the video lectures. Feel free to pause the lectures and make changes to the code and see how it affects the output. Second, there are lots of reading materials that I attach both on slides and in the course notebooks. I believe you can learn a lot by reading through them, so don't miss that experience. Third, there will be coding exercises that will not be graded, but it will give you experience and challenge your understanding of the content explained in this course. Finally, feel free to join the Slack channel of this course to discuss the assignments, share ideas, ask questions, and collaborate with other learners who have taken this course. The backpropagation algorithm is the learning mechanism that allows machines to reach such astonishing levels of accuracy. It starts with input represented as a vector x, that is fed into the network. The inputs are multiplied by the weights of the synapses between the neurons. Then the output of the dot product is summed and passed through a nonlinear activation function that allows neural networks to outperform traditional machine learning techniques in that they can learn a representation for nonlinear manifolds. This is called the forward path. The results are then compared against the ground truth responses using an objective function, the loss, which is then used to update the weights in the backward path using the chain rule for calculating partial derivatives. I would highly recommend reviewing the chain rule from any reference on elementary calculus. In the year 1998, Jan LeCun and his research team published the LeNet5 architecture for handwritten digits recognition. The paper is considered one of the pioneering papers that made it possible to reach the state-of-the-art performance in various deep learning applications. The input image is fed into convolutional blocks. Each block consists of a convolutional layer, a nonlinear activation layer, and a max pooling layer. Then the output is fed into a feedforward network, and finally through a softmax activation to obtain probability distribution over target labels. I have attached the reference to the paper so that you can read it and explore many concepts in depth. Now the coding exercise. Let's start by opening a new terminal window and typing change directory cd Backpropagation PyTorch 2019, and then let's start Jupyter Notebook. This should initialize the Jupyter Notebook inside the directory where the course material is located. We start with section 1. We first start by installing the PyTorch library and the Torch Vision library. You can find the right version for your CPU, GPU, and or your operating system using the PyTorch official documentation on the Getting Started page. Then we run a few tests to make sure that our installation was successful by importing Torch and Torch Vision and checking for the version and checking whether CUDA is enabled or not. In my case, I've got a GPU GTX 1050, and that's why I've got torch.cuda.is available returning true. Don't worry if you don't have a GPU, I will show you how to get that done using Google Collaboratory pages. As a nifty feature of Jupyter notebooks, you can run them remotely using the command on the screen, Jupyter notebook --port, and you specify the port number and then --no -browser, and then you specify the IP using --IP. I use it when I'm running code from my laptop onto the computer machine that has got the GPU installed. This way I can move and have more portability when running machine learning models. If you find any trouble when you are installing PyTorch and if you are using Windows, here you are a reference link for troubleshooting the Windows installation. As we have explained in the previous slides, we are going to implement LeNet5 architecture, which is a series of convolutional blocks. To do that in PyTorch, it is very simple. We import Torch, we define a class LeNet5 that inherits from torch.nn.module, and then inside the constructor we inherit from the superclass using super method, and then inside the constructor method def __ init __ we trigger the parent constructor using the super method, and then we define the network using torch.nn.sequential. We divide the network into two modules, the convolutional part and the feedforward part. I will show you in a few steps why it is done this way. Each convolutional block is defined using three layers: conv2d, relu, maxpool2d. It is worth mentioning that the activation function relu is not explicitly mentioned in the paper originally published by Jan Leku, but it is convenient to add this nonlinear activation to the network to make the layers more robust and versatile. Each convolutional layer takes as a parameter the number of input channels. In the first case, since we are training a grayscale image, the init channels number is 1, and then we use 6 filters, 6 layers, 6 channels in the out channels, and we define the kernel size to be 5 by 5 as instructed in the original paper with a stride of 1, and we instruct the bias to be true. That means this layer will learn both the filter values for the convolutional layers and the bias added to them. Next we apply a nonlinear activation relu, and finally a maxpool2d of kernel size 2 by 2 and a stride of 2. We do the same for the next convolutional block, but with 16 filters, and then we have a third convolutional block with 120 filters, and the output will be passed from here onto the feedforward network. The feedforward network self.fcn is a torch sequential layer with two linear layers. The first one is 120 by 84 and the second one is 84 by 10. Finally, we use a softmax activation to get the probability distribution of the outputs. Now that we have defined the structure of the network, we have to define the mechanism by which the forward path will be implemented. We define that using a method defForward, which takes the self as a parameter, and then the batch, which is the images that to be propagated through the network forward and backward. First, we pass the batch through the convolutional block, we get the output return ret, and we change the dimensions because the output will be 3-dimensional, because convolutional output is always 3-dimensional. So we use the ret.view and we pass it the batch dimension, which is batch.size of 0. That is the number of samples in this batch learning. Usually we use 32 for the batch size, and we use -1 so that PyTorch will figure the rest of the dimensions on its own. But here we know that the output would be 2-dimensional. The batch size by the output from the last convolutional layer of the convolutional blocks. And then we take the return ret, pass it through the feedforward network, and return the output. Because PyTorch does not implement a flattened layer just like the one we have in Keras or in TensorFlow. That's why inside the forward path we have to divide the convolutional blocks and the feedforward blocks into two different blocks, and in between we do the flatten using the view method. As a bonus hint, visualization is very critical in implementing and debugging deep learning models, so I suggest this library hidden layer and install it using pip install graphviz and hidden layer, and then import hidden layer and .build graph, and I pass the new object from LeNet5 architecture we've just implemented, and we pass a patch of one sample, and each image is one channel grayscale and 32 by 32 in width and height. And then when we run this code, it prints a visualization of the network that we've just implemented. We can see here it starts with 5x5 convolution, 2x2 pooling, ReLU, another convolutional block, and it goes on. Interesting, you can see on the left side the gradient path or the directed acyclic graph of the gradients, which starts with constant and shape, and then gather, squeeze and unsqueeze and concatenation, finally till we go to reshape. This is because we have used inside the forward path the method to view with the -1 dimension. So this, when we do this, we append new nodes to the graph of the network that PyTorch applies internally to smoothen its operations, as we explain in the next lecture. The network goes on until we reach the softmax layer at the output. I would suggest that you play around with hidden layer. I have attached the reference to the documentation of this library, and you can use it for visualizing gradients, visualizing loss and accuracy as well. Yann LeCun, head of AI research at Facebook, is a Nobel Prize laureate and a Turing Award winner. I personally follow him on both Twitter and Facebook to stay up to date on advancements in the field. This animation illustrates the performance of LeNet5 on handwritten digits. Here you are a short link to the course discussions. Thank you and see you in the next video lecture.